imagine a place in space where gravity is so strong that it warps the fabric of space-time, trapping even light itself.
Whoa.
We're talking about black holes, one of the most fascinating and mysterious objects in our universe.
Absolutely they are.
Today we're diving deep into black holes, how they form, the different kinds out there,
Right.
and what secrets they hold about the nature of gravity and the universe itself.
Okay.
Welcome to Cosmos in a Pod Space and Astronomy series.
Yes.
I'm so excited to be exploring this with you today.
Me too.
So what exactly is a black hole?
That's a great question.
The name is pretty descriptive,
It is.
but I suspect it's more than just an empty spot in space, right?
Yeah, you're right.
It's much more.
Much, much more than just a hole. Yeah.
More than a hole.
Yeah, think of it as a region of space-time
Okay.
where gravity is so intense that nothing, not even light, can escape.
Oh, wow.
It's like a cosmic trapdoor with gravity so strong that it creates a point of no return.
Intense. But how does something like that even form? I mean, how...
Well, the most common way a black hole forms is from the death of a massive star.
Yeah.
You see, stars, they're these giant furnaces that are constantly battling their own gravity, using the energy produced by nuclear fusion in their cores.
Right.
But eventually that fuel runs out.
Uh-huh.
And when a star much more massive than our sun exhausts its fuel, it can no longer support itself against its own gravity. The core collapses, creating a supernova explosion.
Oh, wow.
And what's left behind is a black hole.
So it's like the star implodes on itself.
Exactly.
Great.
All that mass gets squeezed into an incredibly tiny point
Oh, okay.
called a singularity.
Oh,
And that singularity, that's where things get really bizarre.
oh, really?
It's a point of infinite density
Okay.
where our current laws of physics, they break down.
Oh, wow.
It's a place where we just don't have the tools yet to understand what's happening.
Infinite density. I mean, that's hard to even wrap my head around.
I know, it's wild.
So we have these super dense points in space that just gobble up anything that gets too close.
Yeah.
How do we even know they exist if we can't actually see them? I mean, light can't escape.
All right.
So are we just blindly assuming they're out there?
That's a great question. And
I mean, how do we...
while we can't directly see a black hole, we can detect its presence by observing how it interacts with its surroundings.
Uh-huh.
Think of it like seeing the footprints of a ghost, you know? Okay, you can't see the ghost itself,
Right.
but you know something's there based on the evidence it leaves behind.
I see.
Yeah.
Okay, so what kind of footprints do black holes leave behind? What are we looking for?
Well, one way we detect black holes is by observing their gravitational pull on nearby stars.
Oh, why?
So if a star is orbiting an invisible object that's incredibly massive and compact, well, that's a pretty strong indication that we're dealing with a black hole.
So astronomers, they look for stars that seem to be orbiting nothing.
They do. It's pretty amazing.
That sounds like a tricky observation.
It does. It does.
How do they even...
It requires very precise measurements.
Oh, wow.
But it's a technique that's been used successfully to identify many black holes.
Okay.
And in recent years,
Yeah.
we've had another incredible tool at our disposal.
Oh.
Gravitational waves.
Oh, yeah. I've heard about those.
Have you?
Those are ripples in space-time, right?
That's right.
But how do those help us find black holes?
Well, when massive objects like black holes collide,
Okay.
they create these ripples in space-time
Right.
that travel outward at the speed of light.
Wow.
And we can detect these waves
Okay.
with incredibly sensitive instruments like LIGO and Virgo.
So we can actually hear black holes colliding.
We can. It's pretty amazing.
That's incredible. I mean, it's just
It really is.
so much to learn about these things.
So,
And these observations, they not only confirm the existence of black holes, but they also give us amazing insights into their properties and behavior.
you got it.
So we've been talking about black holes forming from dying stars.
Yes.
But are all black holes created that way?
Well,
Is there only one size or flavor of black hole out there? I mean...
that's where things get even more interesting.
Okay.
Black holes come in a range of sizes.
Oh, wow.
And some of them formed in ways that we're still trying to fully understand.
So what are the different types of black holes out there? I mean, what's out there?
Well, The most common type are stellar black holes.
Okay.
The ones we've been talking about.
Yeah.
They typically have a mass about 3 to 10 times that of our sun.
Okay.
But then we have the real giants of the universe.
Yeah.
Supermassive black holes.
Supermassive.
Yeah.
That sounds pretty intimidating.
They are.
Just how big are we talking here?
These monsters can have masses millions or even billions of times greater than our sun.
Oh, wow.
They're so massive. Yeah.
That they reside at the centers of most galaxies, including our own Milky Way.
Hold on, are you telling me there's a supermassive black hole at the center of our galaxy?
Right in the middle of the Milky Way.
Oh my goodness.
There's a supermassive black hole called Sagittarius A.
Wow.
We can't see it directly, of course,
Mm.
but its gravitational influence on nearby stars is undeniable.
That's both amazing and kind of terrifying at the same time.
It is.
I mean, it's just amazing to think about, but how do these supermassive black holes form? I mean, are they just
Well,
the result of a bunch of smaller black holes merging together, or?
that's one possibility.
Okay.
But it's still a bit of a mystery, yeah.
Really?
Some theories suggest they could arise from the collapse of massive gas clouds
Oh, okay.
in the early universe.
I see.
Others propose they might have started as smaller seed black holes
Okay.
that grew over billions of years, devouring surrounding matter.
Oh, wow. So they just eat and eat and eat and eat.
It's one of the most active areas of research in astrophysics.
It is, absolutely.
So we have these stellar black holes formed from dying stars.
Right.
And these supermassive behemoths lurking at the hearts of galaxies.
Yeah.
Are there any in-between sizes? I mean, what else is out there?
Yes.
Really?
There's a hypothetical class called intermediate mass black holes.
Oh,
These would have masses hundreds or thousands of times that of the sun,
wow.
bridging the gap between stellar and supermassive black holes.
So they're like the middle child of the black hole family.
Exactly.
You haven't definitively observed any yet.
We haven't definitively observed any yet,
Oh,
but there's growing evidence to suggest they might be out there.
oh, wow.
They could form from the mergers of stellar black holes,
Okay.
or maybe even from the collapse of extremely dense star clusters.
It's amazing to think about the variety
Yeah.
of black holes
It is
that might be scattered throughout the universe.
all over the place.
But you mentioned earlier that things get really weird near a black hole.
They do.
What kind of strange effects
Yeah.
are we talking about? What happens?
Well, for starters, if you were to get too close to a black hole,
Yeah.
you'd experience something called spaghettification.
Spaghettification. That sounds kind of unpleasant.
It does, yeah.
What exactly does that mean? What happened?
Imagine being stretched out,
Okay.
like a noodle,
Okay.
due to the extreme difference in gravity between your head and your feet.
Okay.
The gravitational pull
Yeah.
would be so much stronger on your feet than your head
Oh, okay.
that you'd be stretched into a long, thin shape.
I think I'll pass on that experience.
Probably a good idea.
Anything else I should be worried about? What else happens?
Well, there's also time dilation.
Time dilation.
As you approach a black hole, time itself would slow down
Okay.
relative to an outside observer.
What?
It's one of the most mind-bending consequences of Einstein's theory of general relativity.
Wait, so time literally moves differently near a black hole.
It does.
That's messing with my brain a little.
I know, it's pretty wild.
So it's
It's a consequence of intense gravity warping the fabric of space-time itself.
okay.
The stronger the gravity, the slower time flows.
So hypothetically, if I were watching someone fall into a black hole,
Yeah.
what would I see?
You'd see them approach the event horizon,
Okay.
which is the point of no return.
Right.
As they get closer, they'd appear to slow down and redshift,
Okay.
meaning their light would stretch towards the red end of the spectrum.
I see.
Eventually, they would fade from view entirely.
So they would just disappear.
Essentially, yes.
Wow.
From your perspective, they would never actually cross the event horizon.
Okay.
They would be frozen in time.
Frozen in
That's
it. That is why I mean just
It's pretty incredible, isn't it?
I know, but what about the person falling in? What they experience?
Now, that's a question we can't definitively answer
Oh, really?
once they cross the event horizon. We have no way of knowing what happens to them.
Huh.
It's one of the biggest mysteries of black holes.
Wow.
It's a point where our current understanding of physics breaks down.
Okay, that's enough mind-bending physics for now.
I hear ya.
Before we go any further down that rabbit hole,
Right.
let's explore how black holes influence the universe around them.
Okay, sounds good.
They sound like they have a lot of power.
They do, they do.
This is all so fascinating. I can't wait to hear more about it after.
After we take a little break to let all this sink in. How about that?
Exactly. We'll be back soon to continue our deep dive into the world of black holes. Don't go anywhere.
We'll be right back.
All right, we're back and ready to continue our deep dive into this fascinating world of black holes.
All right, let's do it.
Before the break, we were discussing those mind-bending effects of gravity near these cosmic behemoths.
Right.
But now I'm really curious about the bigger picture. How do black holes actually impact the universe around them? I mean, what do they do out there?
That's a great question, and it's one that astrophysicists are still actively exploring.
I bet.
It turns out that black holes, they're far from isolated phenomena.
Okay.
They have a profound influence
Really?
on the evolution of galaxies and even on the large-scale structure of the universe.
So they're not just sitting there passively swallowing things up.
Nope, not at all.
They're actively shaping their cosmic neighborhood.
Absolutely, yeah.
Oh, wow.
Let's start with the supermassive black holes at the centers of galaxies.
Okay.
These giants exert an incredible gravitational pull on everything around them. Stars, gas clouds, even other black holes.
Oh, wow.
This gravitational influence,
Okay.
it helps to shape the structure of the galaxy, guiding the orbits of stars
I see.
and regulating the flow of gas.
So it's like the black hole is the conductor of a giant cosmic orchestra,
Yeah, I like that analogy.
dictating the movements of everything around it.
Exactly.
All right.
But their influence goes beyond just gravity.
Oh, okay.
As matter falls towards a black hole, it doesn't just disappear cleanly.
What does it do?
It forms a swirling disk of gas and dust called an accretion disk.
Oh, so it's like water swirling down a drain, like picking up speed and energy as it gets closer to the center.
Yeah, the analogy is helpful,
Yeah.
but the reality is far more extreme.
Really?
Yeah, these accretion disks, they become incredibly hot.
Okay.
Due to friction and the intense gravitational forces.
Right.
They can reach temperatures of millions of degrees, emitting intense radiation across the electromagnetic spectrum, including X-rays, which we can detect here on Earth.
So it's like the black hole is powering a giant cosmic spotlight.
Exactly. A great way to put it.
Shining brightly in X-rays.
And it gets even more impressive.
Really?
Some black holes also launch powerful jets of charged particles at nearly the speed of light.
At the speed of light?
Almost. These jets can extend for thousands of light years, influencing star formation and shaping the interstellar medium far beyond the black hole itself.
So black holes were like cosmic sculptors.
They are.
Wow. Shaping the structure of galaxies and influencing the birth of new stars.
They are indeed, yeah.
Incredible.
And their impact doesn't stop there.
Really?
Black holes also provide us with incredible natural laboratories.
What do you mean by natural laboratories?
Yeah.
How can we study something that we can't even see directly? I mean,
Oh, right. Well, by observing the effects of black holes on our surroundings, we can probe the limits of our current theories, particularly Einstein's theory of general relativity. For example, by studying the orbits of stars around the supermassive black hole at the center of our galaxy, we can test the predictions of general relativity in a regime of very strong gravity.
So black holes are like a testing ground.
They are.
Of some of the most fundamental laws of physics.
Precisely.
That's amazing.
And it goes even deeper than that.
Really?
What else?
Black holes also force us to confront the limitations of our current understanding at the singularity, where density and gravity become infinite.
Right.
Our current laws of physics, they simply break down.
Oh, wow.
This breakdown highlights the need for a more complete theory of gravity, one that can reconcile general relativity with quantum mechanics, the other pillar of modern physics that governs the behavior of matter at the subatomic level.
So black holes are like a cosmic puzzle, challenging us to find a way to unify our theories of the very large and the very small.
You got it.
Wow.
They push us to the very edge of what we know and challenge us to develop new ways of thinking about the universe.
That's incredible.
And as we continue to study them, I'm sure we'll uncover even more mysteries and paradoxes.
Speaking of mysteries, you mentioned earlier a concept called Hawking radiation.
That sounds like something that challenges our traditional view.
It does.
Black holes as these inescapable cosmic traps.
Right.
Can you tell me more about that? What is that?
Absolutely. Hawking radiation is a theoretical concept developed by physicist Stephen Hawking.
Right.
And it suggests that black holes, despite their reputation as cosmic vacuum cleaners, can actually emit particles.
Wait, hold on. Are you saying that things can actually escape from a black hole? I thought nothing could get past the event horizon.
That's the classical view.
Okay.
But when you bring quantum mechanics into the picture, things get a little more complex.
Okay.
Hawking radiation arises from quantum effects near the event horizon.
I see.
It's a subtle process, but it essentially allows for the creation of particle-antiparticle pairs near the black hole.
Okay.
One particle falls into the black hole while the other escapes, carrying away some of the black hole's energy.
So it's like the black hole is slowly leaking energy, even though nothing can directly cross the event horizon.
That's a great way to think about it.
Wow.
Over incredibly long timescales.
Yeah.
This Hawking radiation can cause a black hole to slowly evaporate.
But you said this process is incredibly slow, right?
Yes.
So we're not talking about black holes vanishing anytime soon.
No, not at all. The evaporation time for a stellar mass black hole is far longer than the current age of the universe.
Okay.
But the implications are still profound.
Right.
It suggests that black holes, they aren't eternal prisons. They eventually give back some of the energy they've consumed.
That's a pretty mind-blowing concept. I mean, just to think about that it's not just a one-way street.
It's not.
So black holes, they're these incredibly complex objects.
They are.
With immense gravity, swirling disks of superheated matter.
Right.
And even the ability to slowly evaporate over time.
It's right.
It's incredible.
It is.
What are some of the biggest questions that scientists are still trying to answer about black holes? What are we still trying to figure out?
There are so many.
Yeah.
One of the biggest, as I mentioned earlier, is the quest to unify general relativity and quantum mechanics.
Okay.
We need a theory of quantum gravity to fully understand what happens at the singularity of a black hole.
So it's about finding a way to bridge the gap between our understanding of the very large and the very small.
Exactly.
Right.
Another major question is what happens to information that falls into a black hole?
Really?
According to quantum mechanics, information cannot be destroyed.
Okay.
But what happens to it once it crosses the event horizon?
Right.
Does it get encoded in the Hawking radiation somehow? This is known as the black hole information paradox.
Okay.
And it's a puzzle that has kept physicists up at night for decades.
It sounds like we're just scratching the surface of what there is to learn about black holes.
We are.
Wow. This is...
Black holes are a constant source of wonder and mystery.
Yeah.
Pushing us to the limits of our imagination and our understanding of the universe.
That's amazing.
And who knows what incredible discoveries await us as we continue to explore these cosmic enigmas.
Well, I, for one, am excited to see what the future holds for black hole research.
Me too.
This has been a truly fascinating deep dive.
It has.
But I think my brain needs a little break from all this mind-bending physics for now.
I understand completely. It's a lot to absorb.
When we return, let's shift gears slightly and explore one of the most groundbreaking achievements in recent black hole research.
Okay.
The Event Horizon Telescope and the first ever image of a black hole shadow.
Sounds great. I'm looking forward to diving into that.
Welcome back to Cosmos in a Pod. We've been on quite a journey exploring the mysteries of black holes.
We have.
From their formation to their those mind-bending effects on space-time.
It's amazing stuff.
It really is. And before the break, we were talking about some of the big unanswered questions surrounding black holes.
Yeah.
But now I'd love to delve into something a bit more concrete.
Okay.
The Event Horizon Telescope and that incredible image of a black hole shadow.
Oh, yeah.
That captivated the world. I mean, that was
a landmark achievement.
It really was.
A testament to the power of human ingenuity and collaboration.
I remember seeing that image splashed across news headlines everywhere.
It was everywhere.
It was such a powerful moment. I mean, to finally see visual evidence of something that had been theorized for so long.
So long.
But for those who might not be familiar,
can
you explain what the Event Horizon Telescope is?
Sure.
And how it managed to capture this elusive image? I mean, how did they even do that?
Well, it's not a single telescope.
Okay.
But rather a global network of radio telescopes.
Oh.
Strategically placed around the world.
I see.
They work together combining their data to create a virtual telescope the size of Earth itself.
Oh, wow. So they're combining all these.
This technique,
Yeah.
it's called very long baseline interferometry.
Okay.
Gives the EHT incredible resolving power, allowing it to see details that would be impossible for any single telescope to discern.
So it's like having a giant eye on the universe.
Exactly.
Capable of seeing the tiniest details from vast distances.
That's it.
And that's precisely what was needed to image a black hole.
It was.
Remember, black holes themselves,
Right.
they're invisible because light can't escape their gravitational pull.
Right.
But the EHT wasn't looking for light emitted by the black hole itself, right?
That's right. It was looking for the shadow cast by the black hole against the bright background of hot gas swirling around it.
So it's like seeing the silhouette of a person standing in front of a bright light.
Yeah.
You can't see the person directly.
Right.
But you can see the shape they create by blocking the light.
A perfect analogy.
Okay, so the EHT targeted the supermassive black hole at the center of the galaxy.
That's right, M87.
M87, a giant elliptical galaxy about 55 million light years from Earth.
Wow, that's so far.
This black hole is a true monster with a mass millions of times greater than our sun.
And what did they see? I mean, when they pointed this virtual Earth-sized telescope at M87, what did they see?
They saw exactly what Einstein's theory predicted. A bright ring of light bent and distorted by the black hole's intense gravity surrounding a dark central region, the black hole's shadow.
It must have been an incredible moment for those scientists involved.
It was.
I mean, to see confirmation of Einstein's theory in such a dramatic way.
It was a triumph of both theory and observation.
Amazing.
It not only confirmed the existence of black holes beyond any doubt, but also provided new insights into the behavior of gravity in these extreme environments.
Wow, and by carefully analyzing the size and shape of the shadow.
Scientists were able to test Einstein's theory with unprecedented precision.
They were.
And what did those tests reveal? I mean, did Einstein pass with flying colors?
Einstein's theory continues to hold up remarkably well.
Wow.
Even in the face of these extreme tests.
Really?
The observations from the EHT were consistent with the predictions of general relativity.
Wow.
Further solidifying its place as our best current description of gravity.
It's amazing to think that a theory developed over a century ago can still accurately describe these cosmic phenomena that we're only now beginning to observe directly.
It is a testament to Einstein's genius.
It really is.
But even though general relativity has passed these tests with flying colors,
right,
we know that it can't be the whole story.
What else is there?
There are still puzzles and inconsistencies that point to the need for a more complete theory of gravity.
Like the need to unify general relativity with quantum mechanics.
Exactly, as we discussed earlier.
Right.
Black holes are a prime example of where those two theories clash.
Okay.
The singularity at the heart of a black hole, where density and gravity become infinite, is a point where general relativity breaks down.
Wow.
And quantum effects are expected to dominate.
So we still need more.
We need a theory of quantum gravity
to
fully understand what happens in those extreme realms.
It sounds like black holes are not only fascinating objects in their own right.
They are?
But they also hold the key to unlocking some of the deepest mysteries of the universe.
I think so.
This has been such an incredible journey, a deep dive into the heart of black holes.
It really has.
From their formation to their mind-bending effects on space-time.
Absolutely.
To those groundbreaking observations of the Event Horizon Telescope. It's just incredible.
It's amazing.
Thank you for sharing your expertise and taking us on this incredible journey.
It's been my pleasure.
The universe is full of wonders.
It is.
And black holes
are
some of the most captivating objects we've discovered so far.
They're up there.
I agree.
Who knows what other secrets they hold, waiting to be uncovered by future generations of scientists and explorers.
I can't wait to find out.
Me too.
And to all our listeners out there, thank you for joining us on this cosmic adventure.
Thanks, everyone.
If you'd like to continue exploring the universe with us, be sure to follow Cosmos in a Pod and subscribe to our YouTube channel for more deep dives into the mysteries of space and astronomy. Until next time, keep looking up.